On July 19, 2024, the global economy didn't crash because of a hacker, but because of a null pointer. This event, known as the Blue Morning, caused a global travel halt, urban gridlock, and a healthcare blackout, resulting in $5.4 billion in damages across 8.5 million devices. The culprit wasn't even code. It was a configuration file, channel file 291, a 40-kilobyte update meant to detect named pipes. This video is an autopsy of how a simple index out-of-bounds exception bypassed every single testing layer at a $60 billion security company. To understand the failure, you have to understand the battlefield. CrowdStrike Falcon lives in Ring 0, the Windows kernel. It is the operating system's brain. In user mode, Ring 3, if an application crashes, it closes. In Ring 0, there is no close application. Windows pulls the emergency brake, resulting in the blue screen of death to protect the hardware from corruption. Falcon is an ELAM driver, early launch anti-malware. It loads before the OS to catch rootkits. This is why the outage was a boot loop. The driver killed the machine before Windows could even start. The system has two parts. The sensor binary is the compiled code engine, which is heavy, robust, and rarely changed. The channel files are light configuration updates. Think of it like a game console. The sensor is the hardware, and the channel file is the cartridge. You just swap the cartridge to play a new level. This architecture exists for speed. When a new threat appears, new definitions need to be pushed in minutes, not weeks. Normally, updates go through N-1 rings. They start in the lab, move to internal employee laptops for dog fooding, then to 1% of users for canary, and finally to everyone. Sensor binary updates take weeks as they are certified by Microsoft and rigorously tested. However, hackers do not wait weeks. CrowdStrike built a rapid response pipe to instantly push channel files, technically just data blobs, to all 8.5 million sensors. However, channel file 291 wasn't just a list of bad IP addresses. It contained an IPC template, complex logic, instructing the driver on how to parse named pipes. The stage was set in February 2024. CrowdStrike introduced a new template type, let's call it Type 21, designed to accept 21 specific input parameters. The C++ code in the sensor was updated to handle this new template. It created a rigid contract. Always look for 21 inputs from this file type. Fast forward to July 19th. A new instance of this template was generated to block a specific attack, but this specific file instance had a defect. The update file only provided 20 input fields. It was missing the 21st parameter completely. The line blurs here because they treated logic as data. The file told the driver how to execute code, but since it was wrapped in a configuration file, it skipped the code deployment rings. The sensor's C++ interpreter wasn't defensive. It trusted the template type ID, saw type 21, and blindly assumed it needed to read 21 values. It iterated through the memory. 1 through 20 were fine. Then, it tried to access the 21st offset, pointer plus 21. That memory address didn't belong to the object. It pointed to garbage or, worse, protected kernel space. The Windows Memory Manager immediately flagged this as an illegal operation, a read access violation. In Ring 3, the app crashes. In Ring 0, the machine dies. The OS halted instantly to prevent data corruption. This resulted in error 0x50. But why didn't the content validator catch this before it was pushed? The logs indicate it passed. The post-mortem revealed a bug in the test code. The validator used Wildcard matching for this template type. It effectively said, if it looks like a template, pass it, ignoring the specific field count. Since this was the fast lane, there was no staggered rollout. At 4:09 Coordinated Universal Time, the file hit all online sensors simultaneously. Within minutes, IT dashboards lit up like Christmas trees. The servers weren't just down, they were looping. The machine boots, loads the bad driver, crashes, and reboots. It never stays online long enough to download a fix. The only way out was manual intervention. Boot into safe mode, find the directory, and delete the file, one by one. Then, there was the final boss, BitLocker. Most enterprise drives are encrypted. You can't just edit files without the 48-digit recovery key. Admins had to log into Azure, find the specific key for that specific server, type it in manually, and then delete the file for 8.5 million machines. CrowdStrike lost 25% of its value in 2 days. Delta Airlines alone claimed $500 million in losses. But the real cost wasn't the stock price, it was the trust. The gold standard of security had just become the single point of failure. So how do we prevent this? First, implement staged rollouts for everything, even configuration files and urgent updates. Start with 1%, then 10%, then 100%. Second, use fuzz testing. Your validator shouldn't just check for happy paths. It should throw garbage, wrong counts, and nulls at the driver to see if it breaks. Third, practice defensive coding. The kernel driver should never trust the input file. It must verify the array length before reading. Always assume the input is malicious. CrowdStrike has since overhauled its QA process. They now treat content updates with the same rigor as code updates. The systems are back online, but the lesson remains. In a distributed system, efficiency is the enemy of resilience. I've compiled a comprehensive kernel deployment safety checklist based on this incident, covering canary groups, rollback logic, and input validation. It's free in the description below. If you want to master the architecture of resilient systems, check out the system design course linked there as well. We dissect a new major system failure every week. Subscribe so you don't miss the next autopsy. Don't let a null pointer be your legacy. Class dismissed.